Okay, so today we're going to start our first rigid motion on its own. That's going to be reflections. So remember, our rigid motions are reflections, translations, and rotations. Those are the only three that preserve angle and distance, or preserve size and shape. Those are your rigid motions, and today we're going to talk about that. So let's get the date up at the top, 10/16/2020. And then let's look at what a reflection is. Isometric transformation. Now you remember that has a synonym to it. Another word or another words for that is a rigid motion. They mean the same thing. Isometric transformation, rigid motion, same thing. In which each point of the original figure, the original is called the pre-image, has an image that's the same distance from the line of reflection as the original point was, but on the opposite side. Now that's a lot of words for just saying if this was the pre-image and this was the line of reflection, this point is the same distance from the line of reflection as this point is. That's all that said. Okay, and that makes sense, but that's the mathy way to say it. So you can reflect over a lot of different things. You can reflect mostly over a line. And really, two of these here are types of lines. Like the x-axis and the y-axis are both lines. So really, there's line reflections and point reflections. And we mostly deal with line reflections. But I'm going to put a fifth one on here, even though there's really an infinite number of lines you could reflect over, but you'll touch on it tomorrow. The line y equals x. And I'm just going to give you a little hint. It's a diagonal line. If you had a piece of graph paper, it's this line right here. It has a slope of 1 and a y-intercept of 0, so it's like a diagonal line. And we'll put that in your memory for tomorrow. So if you reflect over a line, it's just a mirror image. If you reflect over the point, or actually you reflect through a point, it's considered another form of a rotation. But we're going to really focus on this. First fact about line reflections. The line of reflection, right, so right here, the line of reflection, which is this, is the perpendicular bisector of the segment joining every point in its image. Now, had we started the year using the compass and doing constructions, I wouldn't have to explain this as much, but I'm going to start from scratch here. Perpendicular bisector. So let's look at this line I just highlighted here. If you look at all these dotted lines don't really exist, but if you connected A to A prime, you pretended there was a line between them, and B prime, C and C prime, then this line of reflection is the perpendicular bisector. It meets at 90 degrees. It meets every one of those dotted lines at 90 degrees perpendicular, and it cuts each one exactly in half, bisector. So it's a perpendicular bisector of all the pieces that connect them. That's a big concept that we'll revisit over and over throughout the year. Number 2, reflections are isometric transformations, and we know from right here that isometric transformation really just means rigid motions, which means the pre-image and image does not change size or shape, which means distance and angle is preserved. Things that were parallel before are still going to be parallel later. Collinearity just means things that were all on one line before are going to remain all on one line. Lines don't bend. but the most important pieces there, distance and angle measure, size and shape are the same. The third thing about reflections, and this is the unique thing we talked about a few days back, orientation, and that's the way that you name the shape as you go around it. Orientation is not preserved. It's the only transformation, the only rigid motion especially, that is not preserved. Reflections are an example of opposite isometries, but I'm not even going to get into that because we didn't talk about it last time. But if you remember, let's go up to this example again. And if I was going to talk about orientation, if I go A to B to C, A, B, C, I went clockwise. If I take the image after I've reflected it, and I go A to B to C, I go counterclockwise. So that shows that orientation was not preserved. All right, dot paper is just like graph paper, but these should be pretty simple, right? Here is your perpendicular bisector, your line of reflection. I want you to reflect over line M. So if I take point A, it's one dot from the line, so I go one more dot. On the other side, and there's A prime. B, 2. So I go 2 more, there's B prime. And C was 1, so I go 1 more, and there's C prime. If I connect A, B, and C, I have a perfect reflection of the original ABC. And remember that line M turns out to be a perpendicular bisector of those little red lines that I drew just to help me. The red lines, these things here, aren't really part of the reflection. They just help me prove that it is a reflection. This has, I believe, 6 vertices we have to worry about, but it's the same idea. If I take E and go 2, I go 2 more. There's E prime. D would have been 3, so I go 3 more. There's D prime. G, 1. F would have been here. H. And I. And if you connect them all in the same order, you have your image. What if you had to find the line of reflection? This you can almost see with your eyes. You can tell when you have graph paper or grid paper pretty much where the line of reflection is. Your eyes almost tell you that it's right there, right down the middle. That is the perpendicular bisector. Let's say this point and this point are twins, right? Those are the mirror images. If I was to connect those, the pink line would have been my perpendicular bisector. Letter B is just sideways. It was cut that way. Okay. Letter C, same thing. D is a little different, but you can probably figure out that it would be diagonally folded like that. And E would go right down the middle here. So that's how you find the line of reflection, especially when you have graph or grid paper. But most importantly, and let's just look at this one, because it's crooked, I'm going to pick this point. Its twin, or its image, is this point. All right, that's the, after you folded it, they would line up with each other. If I was to connect those two, the line of reflection, the red line, is the perpendicular bisector, meaning it meets at 90 degrees right here, and it cuts that in half. So at the top of the next page, number 3, I already wrote in, I pre-wrote in where A, B, C, D, E, F, and G were located. And now it's telling me to reflect point A over the x-axis. So a lowercase r is reflect, and it's telling you to reflect something over the x-axis, and that thing is A. So let's find A. It's right here. I'm going to reflect it over the x-axis, which means I have to go up 2 to get there, so I'm going to go up 2 more. And that would be A prime, which is the point -8, +2. The next one says -4, 2 is B, and it wants us to reflect it over the y-axis. So find point B, which is right here, and reflect it over, be careful, there's a couple of extra blue lines here. This is the y-axis. So if I go 1, 2, 3, 4, 1, 2, 3, 4. Whatever you do before it, you do after it, there is B prime. So where is that point? There's the origin. Over 4 up 2, 4, 2. We'll do one more together. -6, 7 is point C, which is up here. And it wants us to reflect. This looks a little bit different. It doesn't have an axis. It's saying reflect over the line named M. So the line named M is this thing. But you can have random lines too. It doesn't have to be the axes. So if I took that point C right here and went 1, 2, 3, 4 till I got to M, and then 1, 2, 3, 4 until I go past M, and there's C prime. So it's 2, 8. Now, if you were to take letter D, 4, 4, and reflect it over the x-axis, what's the answer? Letter E, if you took the point 2, 0 and reflected over the x-axis, what's E prime? If you took F, 8, -5, and reflected over line N, where's F prime? And finally, if you took point G, 0, -4, and reflected it over the y-axis, where is G prime? So now you are going to complete the same thing on your own down there, and this is what you'll take a picture of and attach to the Google assignment on Google Classroom.